Today we will discuss about AVL tree. AVL tree is named after its names of its inventors, that is Adelson, Belsky, Landis, AVL. It is a balanced binary search tree. Binary search tree, as we discussed earlier, balanced binary search tree is a tree where left child is always smaller than the root and right child is the bigger than the root. And balanced binary tree is a tree where the height is balanced, that is balance factor of 17 will be height of left child, that is 1 2, and height is right child 1 2, that is 2 minus 2, that is 0. So it is balanced. Balance means the balance factor will be between 0 1 or minus 1. So here in all of this case it is maintained, so it is a balanced binary search tree. So the properties of balanced binary search tree is left child is always smaller, right child is always bigger, and the height is always balanced, that is the balance factor will be between 1 0 or minus 1, and all subtree follow the same rule. So this is the properties of AVL tree. As AVL tree is a balanced binary search tree, so here balancing is required when we create the tree or insert in this tree or delete in this tree. So to maintain the balance we have to rotate the nodes. So this is called rotation, and by rotation we are balancing the height of the tree. So each time it is needed, so it is very important to know about the rotation. So let's start with the rotation. There are 4 types of rotation present here: RR rotation, LL rotation, RL rotation, LR rotation. Now start with RR rotation. Here is a tree. It is a binary search tree, that is 44, 83 and 99. But it is not balanced because balance factor of this is 0. Balance factor of this is height of left child 0 minus height of right child, that is 1. So 0 minus 1, balance factor is minus 1. So it is okay. But balance factor of 44 is left child, height of left child is 0, height of right child is 2. So 0 minus 2, that is minus 2. So it is not height balanced. So we have to balance it. In RR rotation we have to rotate once. In this case this root will be the left child of this child node. So the root will be child of this child. So here is a rotation, left rotation. This will be here. So 83 will be the new root, 44 will be the left child, and 99 will be the right child. So this is the AVL tree, which is height balanced. This is not an AVL tree as the height is not balanced. Like RR rotation, there are LL rotation, that is left left. In left case the root is here. We have to rotate this one. So there will be 17 here, 13 will be here, and the root will be right child of this. So it is maintaining the binary search tree property and balancing the height. So it is an AVL tree. Now RL rotation, that is R and L. So in this case we have to rotate twice. So first intermediate step will be right rotation. So first we have to make it a right rotation. So 55 will be here and 83 will be here. So the intermediate step will be like this. 55 will be here and 83 will be here. And like RR rotation, now we can change it to this tree, that is 55 will be in the middle as root, and 45 will be the left child, and 83 will be the right child. In case of LR rotation, here is also the height is not balanced for 44, that is 2 minus 0, that is 2. So it is not balancing the height. So we have to rotate it. So first we have to left rotate. So 19 will be here, 17 will be here. So 19 here, 17 here. So this is the intermediate step. Now when we rotate the LL rotation, like this we have to rotate this in right rotation. So 19 will be the root, 17 will be the left child, and 44 will be the right child. So in this way we will rotate in each case when the balance is get problematic, that is not in between 0, 1 or -1. Now we want to create a AVL tree with these nodes. When we are inserting each of the node, it is in case of inserting, so this is an example of inserting also. So inserting each node in the tree or create a tree. So when we create a tree with 34 is here, so there will be no child, it is okay. 51, so there will be one right child, there will be okay. But when we enter 42, it will be here. So the balancing factor of this is 0, this is 1, and this is 0 minus 2, that is -2. So it is problem. So it is RL rotation. So we have to make this intermediate state and then we have to rotate it left. So the tree will be 34, 42, 51. So this is the AVLT up to insertion of 42. Now when we insert 24, it will be inserted here. There will be no problem for 34 as it is 1 minus 0, it is 2 minus 1, so there is no problem. The balance factor is between 0, 1 and -1, so there is no problem. When we insert 31, there will be 31 is less than 42, less than 34, greater than 24, so here. So now there is a problem. We have to check the balancing factor from where we insert or delete a node. So here we insert the node, so we have to check the balance from its root. So first we check this root. So balancing factor of this is 0 minus 1, that is -1, and that is 2 minus 0, that is 2. So here is a problem. So we have to balance it. Now it is a left-right rotation. So we have to make it first 31, 24, then we have to rotate right. So this is the intermediate step. Now we have to rotate right. 31 will be in the middle, 34 will be the right child, 24 will be the left child. Now balancing factor for 42 is 1, 2 minus 1, that is 1. So this is okay. So this is the table up to inserting 31. Now we insert 62. 62 is greater than 42, greater than 51. So it is placed here. So when we insert 62, there is no problem. That the balancing factor of 51 is 0 minus 1, that is -1, which is okay. And balancing factor of 42 is 2 minus 2, that is 0, which is okay. So there is no problem. But when we insert 80, the balancing factor of 62 is 0 minus 1, that is -1, okay. 51 is 0 minus 2, that is -2. So this is a problem. So we have to rebalance it. So in this case there is a right rotation. So we have to only once rotation is needed. We have to rotate it once. So 62 will be the root and 51 will be the left child of 62. So this will be the AVL tree after inserting 18. Now when we insert 17, it will not create any problem because balance factor of 24 is 1 minus 0, that is 1. 31 is 2 minus 1, that is 1. 42 is 1, 2, 3 minus 1, 2, that is 1. So which is okay. When we insert 20, we have to slope from its root. So when we insert 20, 20 will be here. 20 is less than 42, less than 31, less than 24, but greater than 17. So it is here. So balancing factor of 17 is 0 minus 1, that is -1, which is okay. Balancing factor of 24 is 2 minus 0, that is 2. So there is a problem. So here we have to rotate twice. The intermediate step in short I have shown here. So 20 will be here, 17 will be here, and then finally 20 will be the root and 24 will be the right child of 20. So this is balanced AVL tree. So after 20 we get this tree. So this is the final tree. To show you more example, I am giving an example of insertion of 26. So when with this table we want to insert 26, we will insert it in this direction. 26 is less than 42, less than 31, greater than 20, greater than 24, 26. Now balancing factor of this is okay. 0 minus 1. This is 1 minus 2, that is minus 1, okay. Balancing factor of this is 1, 2, 3 minus 1, that is 2. So it is not okay. So here is the problem. 31 here we have balancing factor error. So now we have to balance it. Now this is the table. So first we have to check which rotation is needed. It is left right rotation. So we have to first left rotate it. So 24 will be here, 20 will be here, and 17 will be here. So 24 will be here, 20 will be here, 17 will be here, and 26 is as right child of 26. This is the intermediate step. Now we will rotate this from 31. So 24 will be here, left child will be here. So 24 will be here, 31 will be the right child of this, 26 will be the left child of 31, and 20 and 17 are as it is, left child of 24. So this is the final AVL tree after inserting 26. Now I am showing you some deletion operation. So this is our tree. We want to delete in this sequence. So when we delete 1 have no child, so it is deleted as it is, and after deletion we have to check its balancing factor from where it is deleted to its roots. So here balancing factor is 0. Now balancing factor of this is 1 minus 2, that is minus 1 is okay. 12's balancing factor is 2 minus 3, that is minus 1, which is also okay. So it is balanced. Now we want to delete 2. So this is the table. When we delete 2, the table will look like this. Now we check the balancing factor. Balancing factor of 3 is 0 minus 2, that is minus 2, which is a problem. So we have to left rotate it. So 8 will be the root here, and then so 8 will be the root here, and the left child of 8 will be the right child of 3, and 9 will be as right child of 8. So left child will be right child of this. So this is our AVL tree after deletion of 2. Now we want to delete 9. This is after deleting 9. When deleting 9, we have balancing factor of this as 2. It is 1, 2 minus 0. So we have to rebalance it. So it is left right rotation. So we have to first left rotation. So 6 will be here, 3 will be here, then 6 will be here, 8 will be right child, and 3 will be left child. So this is 6 here, 6 first left rotation, then right rotation. So 6 will be here, then left child of 6 is 3, right child of 6 is 8. Now we want to delete 17. So 17 is here, so it is also have no child, so we can delete it as it is. And then balancing factor of 14 will be 0, 20 will be 1 minus 2, that is okay, and balancing factor of 12 is 2 minus 3 minus 1, that is okay. Now when we want to delete 3, so after deleting 3 it will be okay, that is, as the balancing factor of 6 will be 0 minus 1, that is minus 1, and 12 will be 3 minus 2, 2 minus 3, that is minus 1, which is okay. After deleting 8 there will be a balancing problem, so this will be the tree after deleting 8. So here balancing factor of 6 is okay, balancing factor of 12 is 1 minus 1 2 3, that is minus 2. So the problem is here, so we have to rotate it in this way. So left rotation, so we have to rotate 20 here, and 12 will be left child, and left child of 20 will be right child of the root, present root. So now 20 will be here, left child will be 12, and left child of 12 is 6 as it is, but left child of 20 will be right child of 12. So it is like this, and 27, 25, 30 is as it is. So now it is all balanced. Now we want to delete 12. So when we delete 12, we place 6, the left child of 12 in place of 12. So here the balancing factor will be 0 minus 1, that is minus 1, and here that will be 2 minus 2, 0, so it is okay. When deleting 6, 14 will be in place of here 6. So here will be the balancing factor of 20 will be 2 minus 1, that is minus 1, which will be okay. But after deleting 14 in place of 12, the tree will look like this, which is not balanced, that is balance factor of this is 0, 0, 0, 1 minus 1, 0, and this is 0 minus 2, that is minus 2. So here is the problem, so we have to left rotate it. Now we have to left rotate it. 27 will be the new root, 20 will be the left child of 27, and 25 will be the right child of 20, and 30 will be as it is. So 30 will be as it is, 27 is the root, 20 will be the left child of it, and 25 is the right child of it. So this is how we can delete from an AVL tree. Search is as we search in binary search tree. So like 55, we have to search 55, so 55 is greater than 44, so this way 55 is less than 83, so this way 55 is here. When we search 19, 19 is less than 44, greater than 17, so 19 is here. When we search for 20, less than 44, greater than 17, greater than 19, so there is no right child, so there is no 20 present in this tree. So in this way we can search in AVL tree. Now I think you all understand the basic operations of AVL tree. It is more important to check the balance factor each time when we create or insert or delete from the AVL tree. So try practicing more balancing with many more numbers, and try to create, insert or delete from AVL tree. Searching is as it is in the binary search tree. If you have queries or need any detail, let me know in the comment section. If you are working on a problem and you cannot do that, so let me know in the comment section. If you find this video useful, let me know in the comment section, and subscribe to my channel and share to your friends. Thank you for watching this video.